Okay, so let's get started. My name is Neethu Elizabeth Simon, and I'm a solution architect working for ARM, based out from Chandler, Arizona. So firstly, thank you all for coming to attend my session today. This is my 4th year speaking at the Open Source Summit. It's always a joy to come here and share what I have learned with the open source community. So I'll be sharing how we automated the MCP server testing for the ARM MCP server, and thereby engineering reliability for our Agentic system. So this is the quick agenda. I'll cover an introduction on ARM and the ARM MCP server. Then we look into the testing framework that we had used, and then look into how we automated the whole process using GitHub Actions. Then do a live demo of the whole testing framework, and then finally end with conclusion and then Q&A. So before we get started, introduction about myself. As I mentioned, my name is Neethu Elizabeth Simon, and I'm working for ARM, based out from Chandler, Arizona. At ARM, I build and share AI and IoT-based solutions which are optimized for the ARM platform, specializing in the computer vision and the edge application side of it. Before ARM, I used to work for Intel, very similar role, where I would build these end-to-end IoT and AI solutions for different domains, retail, healthcare, and so on, and then come and share that with our external customers and open source communities. I'm also passionate about volunteering, especially on the STEM side with kids, so involved with several nonprofits like the SWE, Grace Hopper, and so on. So let's get started. So when people think about AI, they often think about models, the frameworks, or the latest technologies. But underneath all of that is the AI infrastructure, which needs to scale, adapt, and then run efficiently everywhere. And this is where ARM comes into picture. ARM is uniquely positioned because it is not limited to one place in the compute stack. I'm pretty sure most of you here have at least one device which is running an ARM processor. So ARM is everywhere, from sensors and smartphones to laptops, vehicles, edge devices, data centers, and cloud platforms. So as AI moves from being centralized and experimental to being embedded in everything that we use, the reach really matters, and this is where ARM comes into picture. So that's why I have the future of AI is built on ARM. So now let's look into the MCP server and why are they useful. Most of you would be familiar with LLMs or the large language models, but they do have several gaps. First is they don't have the domain expertise. Secondly, they lack current documentations and best practices. And then lastly, the tool usage is not deterministic. Output can be different for different models, for different kind of prompts that you give. It's going to be different. So it's not deterministic, right? And MCP server addresses these gaps. So what is MCP server? Is Model Context Protocol. It's an open standard. It's like a universal adapter which allows AI assistants to securely connect to external data sources and execute specialized tools. It provides AI models with context-aware capabilities, such as code analysis or a knowledge-based lookup and system introspection. So MCP server, you can think about it as a USB-C for AI applications. And what we developed is the ARM MCP server with this development tool knowledge along with the expert knowledge required to work on an ARM platform. All of this is packaged in one Docker image. So a little bit more into ARM MCP server. It's open source, available on GitHub. That's the link if you want to take a look at that. So the ARM MCP server provides this AI assistance with tools and knowledge specifically for ARM architecture development, migration, and optimization. It includes capabilities like container architecture checking, code analysis, and a knowledge base with content coming from the ARM learning paths, which is again open source and available, and all the other ARM-specific documentations which are available for everyone to use. Now, one of the specialized tasks would be migrating an x86 code to ARM-based code, right? And manual migration can be really tedious here, time-consuming, because a lot of extensive research time is required. Code rewrites are required, debugging, fixing errors, and then obviously documentation. So in comparison, if we can automate the whole process using this MCP server, it's going to make it really efficient, and then it will transform this developer from a tedious code porter or a migrator to a high-level strategic reviewer. So in a nutshell, what is the ARM MCP server, right? So we have integrated it with the several AI assistants that are available currently, the Claude, VS Code, GitHub Copilot, Anti-Gravity, Kiro is from Amazon, Windsurf, Cursor, Codex, and Gemini, and several others we are working on. How do you find our MCP server? It's available in all the popular MCP registries and Agentic integrations. So we have it on the GitHub MCP registry, the Docker MCP toolkit, GitHub custom agents, and the Amazon Kiro powers. What does it have, right? What's inside the ARM MCP server? We have specialized tools, like I said, for checking if the Docker image is compatible on an ARM architecture or not. We have knowledge base, which is coming from our ARM learning path. And then we also provide prompts to help the developers architect on ARM architecture, migrate, or help optimize the entire code base for ARM. So if I'm a developer, how do I use the whole ARM MCP server, right? So the first step, you can see I have the Visual Studio here open, and then if you go to extension, search for ARM MCP server, you can find it as a plugin, just install it. Second step is start the MCP server. Before you do that, make sure you have the Docker runtime running on your system, because that's the prereq. And then the third step, my specialized task here is to migrate my code from x86 to ARM. Right? So I have an example repo here. The link is also provided here. So it's called ARM migration example. If you go and look at there, it's all C++ codes with a lot of x86 specific libraries, intrinsics being used there. So now I am using my GitHub Copilot. I have selected the Claude Opus 4.5 as my model. And then I'm providing this prompt in that step number 4 with specific instructions. I'm telling it, your goal is to migrate a code base from x86 to ARM, check for x86 specific dependencies like build flags, intrinsics, libraries, and so on, and change them to ARM architecture equivalent. So once I provide that prompt, the MCP server is going to do its magic in the back end, and then it's going to make all those suggestions, ask the user, should I modify these files or not, review it, and then make sure you check that what it's providing is correct or not. And then at the end, you get a summary of the changes being made. That's again a place where you can review whether it makes sense or not, right? All the files being modified, what are being modified, what are those intrinsic mappings being used, and so on. So this is the entire walkthrough of how you can use the ARM MCP server for your regular specialized task, like just migrating your code from x86 to ARM. So next, let's look into the testing side, right? So why is the whole MCP server testing really hard? The agentic behavior is non-deterministic by design. As I mentioned earlier, with different models, we can get different outputs. With different prompts, we can get different outputs. These AI agents don't fail like a traditional software. They don't just throw exceptions. They actually drift away. So they can misinterpret the tools, call the wrong functions or behave differently across environments. Secondly, the manual validation is not scalable option. But as the tools grow, as the knowledge base grows, doing manual testing is, it's not scalable. So you have to automate the whole process. And then lastly, simple unit tests, those can miss the failures at those agent tool boundaries. Right? So our goal is not to make the model deterministic, but it is to make this server contract repeatable and testable. Right? So we are verifying the contract between the server and not the wording of the models. And how did we do that is using our testing framework. We use these two open source Python libraries, Pytest and Testcontainers. Most of you who are working with Python would be familiar with Pytest, used for writing the test cases. And Testcontainers is, again, an open source Python library, which provides lightweight, throwaway instances of Docker containers for testing. Now, instead of mocking the MCP server, we can spin up an actual Docker container and run these tests against it. And at the end, the test container would automatically tear it down. So the user or the developer doesn't have to do anything. The test container does it for you. This has several benefits. Right? First is it's realistic testing. We're not mocking the MCP server. We're actually testing based on the server implementation that's running there. Second is isolation. Now, each test run gets a fresh container instance. Every time we have a new environment, the server starts up, it cleans up, and then it's done. So the next piece is reproducibility. Every time we test, it's going to behave the same way, right? Because even if the CI environments are different, it will behave in the same way because of the test containers. And then lastly, there are no external dependencies. We don't need any particular pre-deployed server or any such setup to do this testing. So we are running the same server, which we are going to ship. Right? Instead of mocking this entire interaction, we will be running the same server that we are going to use. And how are we doing this? Is Pytest. Right? Pytest defines those repeatable scenarios and assertions. The test containers launch the real MCP server in Docker. And then each run would use a clean, disposable environment. So in that way, it's making it more reproducible without any external dependency. Now, how does all of this work? It's the MCP communication, which happens through the JSON RPC 2.0. over the standard input-output or the STDIO transport. So it's the client-server interaction that we are verifying. Right? There needs to be a stable contract. We're not testing the output of the model, not the wordings that are coming out from the model. We are testing that contract between the server and the client. Right? So suppose, so you can see here, I have the Pytest, which has all the test cases. I have the test containers, which are going to create those Docker containers. And then it will start the containers. And whenever the Pytest initializes a request, it's going to send that as a JSON message to the MCP server. The output that we get is again a JSON format. And we already know what is to be expected from there. So that is deterministic. And this is where we make the comparison. Right? And based on that comparison, we can assert whether the test case failed or if it's a success. So in this way, we are making it more stable and deterministic. So this is on the testing framework. And now let's look into automating the whole process. Right? And what do we use here is the GitHub Actions through CI. Every time there is a pull request, we check out the code. We set up our runners, the ARM64 runners. We build the containers, start the MCP server. We run all these Pytest and publish the results. And the test container is going to clean up everything for you. And then finally, if everything works, the PR gets merged in. right? So the CI is actually making the reliability enforceable. Every pull request exercises the full server path before it gets merged. And the contract regressions can surface before the review actually happens. So reliability becomes a release gate here. Now we are also testing the whole thing on an x86 runner as well, not just the ARM64, just to make sure that everything is working and nothing is broken. And so that's it on the presentation, and I can do a demo now. So let me just change the setting. Mirror my desktop. Okay. Let me know if I need to zoom in a little bit more. Okay, so this is our GitHub repo, and the README is right here. The first step is basically build the Docker image, right? So I already built the Docker image because it does take a little bit of time. So if you can see here, I have Docker desktop running. I have my images, the ARM MCP server here, and then I also have a test container image right here. So let's go back to the Visual Studio. So once we have the image built, next step is to install all the requirements, right? And if you see, we only have 2 requirements, test containers and Pytest. Only these 2 needs to be installed. And after that, we just run the test. So I'm going to show the test file. The most important thing here, I can zoom in a little bit more. Is it a little better? Okay. So the most important piece here is this code here. This actually shows you how the test container gets that Docker image name, and then it starts that MCP server. And when while the server is running, it's running all the test cases using Pytest. Okay. And then if you go down, we can see we are testing if the server has come up or not. Just the response from the server, doing an assertion for Pytest. And then if you come down a little bit more, you can see these are the tools which we are testing, right? So we send a request here. The request, we have it here. This is a very simple request. We are checking if this Ubuntu 24.04 is supported on ARM architecture, right? And we know what the response should be. So we already have the expected image response here. So if the server is not sending us the same thing, the test case just fails there. Okay. So I can now just run the test here. And you can see as soon as the test runs, we have 2 containers which automatically got started. One is the ARM MCP server, and the other one is the test container. And then you can see once all the tests are run, these 2 would automatically get tear down. Live demo issues. Okay, for some reason it got stuck. Oh. Okay, something happened. Huh? I should have gone for a recorded demo. Let's try again.
Sorry, you're in a room full of engineers.
Okay, it looks like it's having issues. Anyways, it works. So it's there on GitHub, so you can make sure it works. Okay, so I have just one more slide. Let me go back. Okay. Okay, so the last slide is the conclusion. So what I want to say is treat your MCP server just like a production infrastructure. It's not a demo. It's not a glue code. It's a service that deserves real test. So the containerized integration test will turn a fuzzy interaction surface into a stable engineering contract. And the CI makes that contract enforceable on every change, not just checking it manually, but you're automating it now using CI and GitHub Actions. And this is how your agentic systems become reliable enough to trust. And that's it. Thank you. I have two links there. One is the GitHub repo, and the second one is our ARM learning path. If you want to know more about the Pytest and Testcontainers, how to work with that, the second link is will take you there. If there are any questions, I can take those. Yeah, Mike.
So here, like you said, you focused on the contract with the MCP, but also, as you talked about before, it's really the drift of the agents that is the thing that we're worrying about. And that's sort of a harder thing to test, right? Do you have any things that you're thinking about or suggestions in terms of how we think about testing the agent interaction given the contract, especially since some things that are part of the MCP itself are going to be stuff like how do we tune what prompt and how we're advertising the tools?
Yeah. So one idea we have is to give those prompts to the user, right? So we are guiding the agent to look in that direction, at least to avoid that little bit of the drifting piece that you just mentioned, right? And this is something we are still exploring, so we are also learning. So, yeah.
Thank you.
Any other questions?
No? Okay, thank you.